Today we're going to discuss dimensional analysis. The key to dimensional analysis is this sort of obvious statement that your answer cannot depend upon the system of units that you choose. Units are something they're man-made. We select what we want to call a kilogram or a meter or a second, and therefore physical results cannot depend upon those quantities. And so we'll give several examples here, but that's basically the key to dimensional analysis. So in what precedes here, we're going to distinguish between a few things, what we call fundamental units and derived. Now this distinction is a little bit arbitrary, but what I'll refer to as the fundamental units are mass, length, and time, because they're all independent of each other. Something has mass, which I'll denote by brackets and an m to be the unit of mass. I'm not going to specify that our mass is in kilograms or pounds or grams, but we'll just use m, l, and t to denote mass, length, and time. An example of a derived unit from these would be force, ml over t squared, mass times acceleration. Now, of course, this distinction between fundamental and derived is a little bit arbitrary. I could move force up here and mass down here, for example. There's nothing stopping me from doing that. But I find it easiest to think of mass, length, and time as our fundamental ones and everything else derived. These units here will be sufficient for problems in mechanics. For thermal problems, we might need to think about temperature, but let me hold off on that discussion for now. So the key result that we're going to use in dimensional analysis is something known as the Buckingham Pi Theorem. And the Buckingham Pi Theorem states that if a problem has n parameters expressed in r independent dimensions, then there's n minus r dimensionless parameters that really matter for the problem. It's difficult to understand what this statement means, so I'm going to show you several examples, and by the end you'll sort of get it. Let's start with a simple pendulum. This is the first example everybody does in dimensional analysis, so let's not be original. So we're going to have a mass m hanging on a strength of length L, initially pulled back an angle theta naught, and then gravity will be pointing downwards. So I'm going to pull this back, I'm going to let it go, and we're going to ask the simple question, what's the period? So the way I'm going to proceed using dimensional analysis is I'm going to write out all the parameters in the problem, and I'm going to start with a thing that we want to know, so the period. So I'm going to denote that as the time that it takes to complete one swing, having units of t. So I'm going to write out a little table. So here's the thing we want to know. Then I'm going to list all the parameters that the problem depends upon and their units. So we have the parameters mass, gravity, length, and initial angle. These have the units that I've written here, and for initial angle, I've written none because the initial angle will be measured in radians, which is already a dimensionless quantity. And now what I'm going to do is I'm going to proceed and I'm going to eliminate the different units. So I'm going to eliminate mass, length, and time from the problem just by sort of forming ratios or products of different parameters. So let me just show you how it proceeds. So I'll write out here for each row, eliminate, and we'll start with m. So I'm going to eliminate mass from the problem. Now this is kind of a little bit of a tricky one because there's only one parameter that has the units of mass in it, right? There's nothing here, nothing here, nothing here, only the mass m. So that tells us something quite simple right from the start, which you might have already guessed or known, which is the mass of the pendulum does not influence the period. And we can see that simply from the units because there's no way for me to remove m from the problem. So we've gotten rid of one parameter. Okay, so now we're down to four things. The period as a function of gravity, length, and initial angle. Let's eliminate length. So I can form the ratio g over L, which would have units 1 over t squared. I remove L from the table. And now I've removed length from the problem. Now let's eliminate t. And now I have sort of choices of the way I can write this, but what I'll choose to do is write t squared g over L. And that has no units. So what the dimensional analysis tells me is that the parameter t squared g over L is some function of the initial angle theta naught. So this has reduced the problem quite significantly because before I had 1, 2, 3, 4, 5 parameters expressed in 1, 2, 3 dimensions. So that tells me there's two dimensionless parameters, this and this. Now the analysis doesn't tell us what this function is. That had to come from experiment or some other analysis, but it tells us that these two things are related. If the initial angle was always the same, so I always pulled it back, say to like 45 degrees, then that would tell me that t squared g over L is a constant. We don't know what this constant is from our dimensional analysis, but we know it would just be a constant. Or we could write that as t is some constant that we don't know is a function is equal to the square root of L over g. So a result you might seem familiar. And we came about this result here that things ought to vary as L over g simply by considering the units of the problem and eliminating things to this table. What we'd observe experimentally what this means is if I take a pendulum and I make it 4 times as long, it ought to have twice the period. Okay, so we just did dimensional analysis on this problem where I said that the period is a function of the length, the mass, gravity, and the initial angle, and we figured out what that was. Except I sort of glossed over one detail, which is how do we know what are the parameters? Isn't it possible the period also depends upon friction at the pivot point, air resistance, the mass of the string, the diameter of the string, the material that the string is made out of, maybe the size of this? How do we know initially that it was just G, L, M, and theta naught? Well, this is the real trick of dimensional analysis, and one that I think is glossed over in a lot of textbooks, is they just present the procedure, but they forget to mention that it takes real physical insight to know what the proper parameters are. And so the real trick to using dimensional analysis is to know which of these things we can safely neglect and which ones we can't, and kind of being able to say, okay, well, let's just make an assumption. Let's assume these parameters don't matter. Let's see where that leads us. We'll conduct an experiment and see if reality is matched with that. These are kind of the ways that we'll use dimensional analysis in the course. But for now, we're going to focus mainly on the procedure. But I want you to remember in the back of your mind that dimensional analysis is hard, not because the procedure of eliminating the units from the problem is difficult, but because knowing what parameters to include in your model and which to ignore is really the thing that's really actually quite challenging. So this will be one where you'll start to note that you actually have to know some physics to actually get anywhere. So let's consider I have a sphere of diameter d moving through a fluid with a velocity u. The fluid has a density rho and a viscosity mu. Now, we haven't talked too much about fluids yet in any of these lectures, but we'll learn later that these are really the 2 parameters that matter in what's called a Newtonian fluid. And why only these 2 parameters matter and not, say, the surface tension of the fluid, the speed of sound in the fluid, or all sorts of other things, is, again, going back to this point that when you do dimensional analysis, knowing which parameters to include and which not to is really the key. So now we're just going to sort of focus on the procedure, and I'm just going to tell you these are the parameters that matter. So let's just do the procedure. Actually, let's do something else first. Let's count. So we want to know the drag force, and it's going to be a function of diameter, velocity, density, and viscosity. So we have 1, 2, 3, 4, 5 things, 5 parameters expressed in 3 dimensions, because we're going to find these have only mass, length, and time. So the Pi theorem should tell us that there should be 2 parameters left when we're done. So now let's write out our table. So now we haven't discussed viscosity much, but it has units of m, L over t. So now we're going to do the elimination. You can start with anything you like. I'm going to start with m. We see that we have m here, here, and here. So I'm allowed to sort of form any ratio I want. So I can divide the force by the density or the viscosity. Which you choose is essentially arbitrary at this point. I'm going to pick one, but this isn't necessarily the right or the wrong answer. We could pick the other one, but I'm going to divide the force by the density. And if I look carefully at the units, what that will give me is something linked to the 4th over time. That doesn't have mass in it, so I'm just going to drop it down. That doesn't have mass in it, so I'm going to drop it down. And now I could form a ratio here as either u over rho or rho over u. I don't care what you do. I'm going to do mu over rho. And that will give me something, if I look at it carefully, length squared over time. All right, so we got rid of mass from the problem. Now let's get rid of time. So I see I've got time here, here, and here. So again, I have sort of choices in the way I want to do it. I could move this thing over here to eliminate time. I can move the velocity. I'm going to do the velocity. And actually, as I look at this, you might have noticed I made a mistake. So this is something else important about dimensional analysis. So you need to be careful. So that should be a time squared. Okay, so now let's move the velocity over here, which to get rid of time I have to use u squared, and that leaves me something that has units of length squared. And I'm going to divide by the velocity over here, so I'm going to remove it from our list and write. So now I only have parameters that have length in it, so the only choice now is to eliminate length. And the result I'm left with is that the force divided by rho u squared d squared is some function of rho u d over mu. Now our table gave us the inverse of that, but I wrote it this way because this is the most popular parameter in all of fluid mechanics. It has a special name. It's known as the Reynolds number. We'll talk about it quite a bit. And if you think about this result for a minute, it's actually quite remarkable because what it tells us is that we had this sort of complicated problem where in general, if we wanted the drag force, I might have to consider spheres of different sizes, moving at different velocities, moving through different fluids. But now we see that all the experiments collapse to a single master curve. So I just need to do one set of experiments with one ball at maybe a set of speeds, and I would capture all the data on a single master curve. Now it turns out this master curve, meaning this function right here, is actually quite complicated. It's very hard to know what it would be from any sort of theory, even though it is possible. It turns out to be an easy thing to do experimentally. What's observed experimentally is that if we plot this parameter, which actually we would call the drag coefficient, as a function of the Reynolds number on a log scale, we see sort of two regimes. One is we see this slope, which is proportional to 1 over the Reynolds number. That will kind of tail off, and then it intersects with another curve that is relatively flat. So we have a regime where it's actually quite constant with Reynolds number, and it'll kind of transition from one to the other. And then when we get out to sort of further, and then again, this is a logarithmic scale, so this transition might happen somewhere around a Reynolds number of 10, somewhere out here, maybe around 10 to the 5th. There's this kind of funky dip and kind of some funkiness that happens out here, which is something that actually would be very hard to predict a priori, but is something that shows up quite clearly in the experiments. And so what's cool, though, is we've got this master curve. So we can find this curve once experimentally, and then we can use it for all experiments that we might want to do between now and time immemorial. So now let me show you how you can use dimensional analysis to sort of explore sort of different physics of the problem, though a little of this might seem sort of premature because we haven't discussed fluid mechanics very much. But dimensional analysis allows us to make assumptions and kind of see where it leads us. So let's consider the exact same problem we just did, where we have a diameter d sphere moving through a fluid with a velocity u. But I'm going to consider that only the viscosity is important, that the fluid's density doesn't matter. And what we'll see later is that this is kind of an important regime. So it turns out when the Reynolds number, which again is rho u d over mu, is much, much less than 1. What the Reynolds number really means is it's really inertia of the fluid, the tendency for the fluid to want to keep going, divided by viscosity. And so when the Reynolds number is much, much less than 1, it means the fluid's inertia doesn't matter much, and the forces due to viscosity are much, much greater. And so what that means is the viscosity of the fluid to resist motion exceeds that of sort of pushing the fluid out of the way. And so this is sort of an important regime, and it's one where the fluid's viscosity matters, but its density doesn't. So we're going to really just assume. You have no reason to believe me at this point that this should be true, even though it is, that the force is a function of u d over mu. And so what that tells us is now we have 1, 2, 3, 4 parameters expressed in 3 dimensions, m, l, and t. So we're just going to be left with 1 parameter. So now rather than explaining stuff, I'm just going to write the table and just sort of do my little algorithm, and then we'll talk about the result when we get to the end. So the result is if the fluid's density doesn't matter in changing the and setting the drag force, that the parameter force divided by mu, viscosity, u, velocity, times d, has to be a constant. Cool. Let's save that result and we'll come right back to it. Let's consider another limit. So it turns out when the Reynolds number is large, that inertia matters. So remember, the Reynolds number is inertia over viscosity. So when inertia matters, then the fluid's density matters, but its viscosity doesn't. And again, you have no reason to believe me, so let's just assume, just for the sake of argument, that the force is going to be a function of u, d, and rho. So we'll just assume that, and let's just do the table and see where it leads us. So, if viscosity doesn't matter, but density does matter, then force divided by rho u squared d squared would equal a constant. So let's put all this together, the past three results. So in general, the force divided by rho, velocity squared, diameter squared, is some function of the Reynolds number that we can determine from experiment. The viscous result, where we said the density of the fluid doesn't matter. The force divided by mu u d is some constant, I'll call it C1. And another way of writing that is I can multiply both sides of the equation by mu over rho u d, or divide it by the Reynolds number. And you see now some stuff cancels out. And what I'm left with is that the force divided by rho u squared d is some constant over the Reynolds number. So I'm just trying to get my force in the same form. And when we considered the case where viscosity didn't matter but only density did, so the inertial regime, we derived that F over rho u squared d squared is a constant C2. Now let's go back to the picture I drew a while ago, which is we're going to plot log of the Reynolds number here versus log of the drag force, or F over rho u squared d squared. And remember, I said the experimental data looks something like this on a logarithmic scale. And so what we find is in the experimental data for the general problem is that when the Reynolds number becomes small, much, much less than 1, that we have a functional form, which is some constant divided by the Reynolds number. Now it turns out this constant, you can measure it, or you can determine it from some other theory, but dimensional analysis just tells it ought to have this functional form, and that is in fact what the data show. And the inertial regime tells us that F over rho u squared d should become a constant, which again, the experimental data show over at least some regime. And then there's something funky that happens out here, which no dimensional analysis can explain. So what the real sort of point of doing this, because we're sort of jumping ahead of ourselves, is sort of talking about this physics of low Reynolds number and high Reynolds number, viscosity, inertia, is that really what we've done here is we've shown that dimensional analysis alone gives us the drag force as a function of Reynolds number as a single master curve, so all experiments are collapsed on this single curve. And that if we go ahead and make assumptions that there might be regimes where certain parameters matter or don't matter, we can even make the problem even simpler and often find some sort of limiting behavior. Now, if we did this analysis here where we assume the viscous regime and the inertia regime, but we couldn't find those on the plot of the experimental data, then we would just trash that and say, well, that was a silly thing to do. I should never have done that. But when we look at the experimental data, we actually find that it's there, so we're pretty happy that our interpretation of this regime out here means we're in a regime where density doesn't matter. When we're in this regime here, it means we're in the regime where viscosity doesn't matter. So pretty cool, right? Let me just make a few more comments. So in some books, when they had this problem, they'd say, okay, so the drag force is some function of diameter, velocity, viscosity, and rho. And then what they would do is they'd follow this procedure where they sort of say, okay, let's assume d is to some power alpha, u is to some power beta, viscosity some power gamma, blah, blah, blah. And they go on, and they basically do the same thing we did in the table method. You're allowed to do this, and you're allowed to read a book that does this method, but I would advise against it. I find this method extremely confusing. I think the table method is kind of straightforward, because usually we're just talking about sort of dividing one factor by another or a square. So if anyone tells you this is the right way to do them, tell them I said no, it sucks, I don't like it. So that's my first comment. My second comment is that dimensional analysis is hard. The procedure is easy, but knowing the right parameters to include and what not to include is not. It takes a lot of physical insight to use it sort of properly. So rather than giving several more examples, I think we'll just conclude here. Dimensional analysis is something we'll sort of continue to use throughout these lectures and throughout the course. And so you'll see many, many more examples of using it. And as we do, what you'll do is you get more and more insight. You'll find that learning the right parameters to include, it gets better, right? So once you start getting some physical insight, sort of doing the procedure and being comfortable including and excluding certain parameters, it starts to seem less of a black art. But I think a lot of books make it seem like, oh, it's real easy because there's this kind of procedure, we just eliminate the units, the pi theorem. I think that's sort of glossing over the detail that knowing the right parameters to include is really sort of the key and actually a very difficult thing to do. So let me just conclude by showing you something in a textbook on dimensional analysis from 1922 by Bridgman. This is actually really a quite excellent book. And I won't go over the whole thing, but he's discussing a sort of exchange in the journal Nature between two people, one of them being Lord Rayleigh, whose name you've probably heard attached with many, many things. But they're sort of going back and forth about this sort of famous article that Lord Rayleigh wrote in the early 1900s about the use of dimensional analysis, or what he called similitude. But they sort of have this back and forth that he's sort of discussing here in his Bridgman's discussing in his textbook. But I just want to point out this one quote. He says, "This reply of Lord Rayleigh is, I think, likely to leave us cold. Of course, we do not question the ability of Lord Rayleigh to obtain the correct result by the use of dimensional analysis, but must we have the experience and physical intuition of Lord Rayleigh to obtain the correct result also?" So this is really getting at that point. The dimensional analysis is hard, not the procedure of eliminating the units, but knowing which parameters to include.